Hello, everyone, and welcome to the MLOps Live webinar series. My name is Sahar, and I'm the VP Marketing at Iguazio. I'm delighted to welcome you to another webinar dedicated to operationalizing machine learning and bringing data science into real business applications. Working with customers across different verticals, we often find that one of the challenges keeping companies from deploying AI effectively, and especially at scale, is the fact that data science, engineering, and DevOps teams often work in silos, completing one part of the project and passing it over to the next team to do their part. This method creates lots of friction and complexities, because the truth is that the only way to deploy AI at scale in an effective way is to have working processes that foster collaboration, end-to-end, and the right technologies to enable that collaboration, and to automate many of the complexities of MLOps. And to guide us through this topic today and share from his experience in bridging these silos and building processes that bring these teams together, we're thrilled to have Greg Hayes with us. Greg is the Director of Data Science at Ecolab, the global leader in water, hygiene, and infection prevention solutions and services that protect people and vital resources. Ecolab works with food, healthcare, hospitality, and industrial markets. And Greg leads the global initiatives for advanced analytics platforms and MLOps at Ecolab, working regularly with Python, Kubeflow, Dask, and Azure. He has experience leading global innovation and R&D initiatives across all stages of the development lifecycle. Greg is going to tell us how Ecolab is accelerating the deployment of AI applications by using new MLOps methodologies, leveraging microservices, and building easier processes for the teams to create a culture of collaboration. He'll also touch upon overcoming political, cultural, and technological barriers to adopting new ways of working on data science projects. Greg will be joined by Iguazio's co-founder and CTO, Yaron Haviv, a serial entrepreneur who served in multiple CTO roles before starting Iguazio, and also created Nucleo, a leading open source serverless platform with over 3,000 GitHub stars, and MLrun, Iguazio's open source pipeline orchestration framework. Yaron will be discussing agile development and continuous delivery of machine learning to production, and he'll also be showing us a live demo. We're going to hold a Q&A session, so you can feel free to post your questions on the Q&A panel at the bottom of your screen. And we'll also be having an Ask Me Anything session immediately after this webinar on our Slack channel. So we invite you to join the community, and we'll share the Slack link a bit later on. We are recording this session so that we can send you the recording afterwards. And we've now put everyone on mute so that we can get started. And Yaron, I will pass the virtual mic over to you.
Okay, thanks, Sahar. Let's move to the next slide. So hi everyone. We're really glad to have Greg here to talk to us about his experience. Greg is very experienced and is also pretty innovative in his approach to address data science. So I think it's important for everyone to listen to their experience. The problem that we're trying to look into here is that if you think about traditional machine learning, is about doing things in exploration in the lab, where you have all those different steps, extracting some small data, then running some small scale preparation on your notebook, and then trying to run training and so forth. And the real challenge is that when you want to productize it and create it, as Greg calls it, the data product out of the artifacts that you build, the model, the data engineering code, etc. It's a very big task that needs to involve using real data coming from streaming, from various operational databases through ETL, from APIs, running preparation at scale, not inside a notebook, but rather using distributed frameworks, then running training with various permutations, parameters, AutoML, etc. And finally doing like serving of the model along with the APIs and the real-time features that require to serve the model. And with that, there's also a feedback loop of things like drift detection, etc. And all this operational pipeline is usually a huge effort that is starting from scratch. Next, Sar. So the general idea is how to build this workflow when someone builds something in his laptop, in his PyCharm, Jupyter, or his IDE? How do you try and make it production worthy with as little steps as possible without necessarily throwing away the code and restarting from scratch in a different framework? And the things that you have to do in order to productize the code is the things that you see here, like packaging your code inside containers or microservices with all their dependencies, and then figuring out if you need to process lots of data, as Greg will show us, you need to think about parallelism. And there are frameworks for doing so, but how do we integrate with those frameworks? And then you need to think about tuning and performance to essentially make it more cost effective and address the required SLA of the real application, followed by instrumentation for tracking everything we do so we can go back in time and figure out why we have certain results, or we can explain our results for audits or any other reasons. And we also want to automate the entire workflow. So when we deploy something to production, we use the concept of CI/CD and automated deployments while everything is live. So all those different tasks take huge amount of effort and energy and time. And part of the thing is to see how you do all those things in a more automated fashion. Next. So the general idea is how to build a pipeline where you collect the data from a variety of sources, you do the preparation in a larger scale, run the training followed by preparing the relevant features from a feature store, and then figure out how to deploy that all on a single distributed system. Next. So with that, we'll start some polls, but following that, we'll start with Greg's presentation. Sarah?
Yes, thank you, Yaron. So we really want to hear from everyone here what your current process of collaborating across data science, engineering, and DevOps looks like. So please fill out the poll, which you will see in a moment. And there it is. This is to help us make these sessions as valuable as possible for you. And of course, we'll share the results with you all at the end. So we'll just give it another 5 seconds. Great. Thank you, everyone. And we are moving on to Greg.
Can you hear me?
Yes, please take it away, Greg.
Okay. Thanks, Sahar. Thanks, Yaron. So to give a little bit of context, where data science fits within Ecolab, as Sahar mentioned, Ecolab is the global leader in water, hygiene, and infection prevention solutions and services. We have over 45,000 associates in the organization, over half of which are in our field and service teams. They go out to our customers every day. We have millions of sites that we visit, and millions of devices that we have deployed that are collecting telemetry, and we're bringing back to generate insights on the order of 8 million data points or more a month last year. And our real goal here is to figure out how to generate insights that help enable our customers and our field associates make the world cleaner, safer, and healthier. About 1.5 years ago, as Yaron mentioned earlier, we were looking at the question of how do you improve the success rate of data science projects? Not just the number of projects that you take to production, but the speed with which you get them into production. I think it's well documented across the field that a model can be built in 8 to 24 weeks, roughly. Estimates vary, but assuming you have data, good data, and you can build a model, it takes about that long. But many organizations are taking 18 months or more to get models into production, and that's a gap, and I think it's one everyone's trying to address. And about 1.5 years ago, we went down this path of systematically trying to understand how we could address these challenges. So with that in mind, let's start with the question of what does it take to model, to move a model into production? What does that really mean? So for the purposes of this discussion, we're going to start from the assumption that constructing a model is technically feasible, and we're really trying to answer the question, what does a successful deployment look like? Okay, so our first assumption here, our first target is to make sure that we understand the business context of and the value of the model that we're going to put out. And we need success metrics. Deploying models into production is not free from both a cost and a resource perspective. And if we're going to undertake this endeavor, we need to understand what we expect to get out of it. Second, and very importantly, we need to be able to articulate what our strategy is for integrating our outputs into a product. Models in and of themselves are not consumed in isolation. These items need to be integrated into components and the results need to be delivered out to customers or consumers, either internally or externally. Finally, we have to have a defined process for supporting, versioning, and extending the product that we end up building in a production setting. We need to be able to answer the question, who will get the call at 2 a.m. If or when something breaks? Is our code written in such a way that it can be easily understood by other team members, or is there a single person in the entire organization that's capable of retraining and supporting the model in production? Do we leverage best tools, common best practices for creation and deployment, or does every team member take their own approach to writing and deploying code? We need strategies around automation, alerting, SLAs, availability, and what tools are we using to verify that our code performs as expected? These are all required best practices for building any sort of digital product. Models are no real different, not really any different here. Next slide, please. If we step back and we think deeply about some of these ideas, it becomes apparent that as much as we as data scientists want to focus on the newest tools and algorithms, the opportunities before us are heavily weighted toward how we work, and the technical components should be chosen to align to support those needs. With this in mind, let's first consider shifting our focus toward creating data products. If we focused first on the creation of products as outcomes rather than models as outcomes, then we have to recognize that successful products get built by teams of people across many different functional areas within an organization. This precludes the idea of our data scientists working in isolation, but instead forces us to consider embedding our teams as part of a larger overall team to ideate, create, and build products. We also need to seek to get better alignment and transparency with stakeholders around the creation of the digital products. This is where adopting tools like Agile development really shine. Over the next few slides, I'll provide some thoughts on how evolution of data science teams within a business occurs, how these patterns manifest themselves with respect to deployment. One argument against data science in an Agile approach is that data science is a discipline of innovation, which can be true, but even when it's not, as a field, there's this belief that practitioners should not be constrained by structures like timelines and deliverables. Unfortunately, what innovation leaders have learned through the study of things like design thinking is that innovation thrives when it's forced to occur within constraints. So we actually get better when we time box our work, when we focus our effort carefully. So as the last bullet here, we need to embrace tools and techniques that simplify the migration from exploration to production. Current approaches, which often consist of teams exploring in one language and then rewriting to deploy in another, or creating point solutions on a per model or even worse, a per customer basis, add cost. They're prone to error, they increase risk. So where possible, we need to leverage the original code written by data science teams into production grade languages and layer in the discipline of best practices around software engineering. That should be the goal. Next slide, please. With these ideas as a backdrop, let's consider how data science teams seem to evolve across organizations. And this is really a question, I think, sometimes of maturity, but it's one worth considering because these different emergent practices have an impact on how we work, the tools that we choose, and ultimately, I think, the success of the products in moving to production. In the emergent data science project or process, data science teams oftentimes work in isolation. They're really expected to own, and you see there's really one stakeholder here bar across the bottom, own the entire process from idea to deployment. This might actually be where the genesis of that mythical data science unicorn came into being. Two things to note in this scenario, if you select the next. So these are all the stakeholders that you probably need to have some level of engagement with, or some of the stakeholders that you probably need to have some level of engagement with to get your model into production. And they're really not part of the process in a coherent way in this pattern. The other thing you note out of this is there's no clear path to deployment. We don't really know how we take our model into production. So, you know, in this pattern where you're working heavily on local compute, ad hoc data access, disorganized stakeholder engagement, it only worsens the challenges of getting a model into production. So what oftentimes ends up happening is your team gets frustrated, and rather than moving to deploying the model, they'll circle back and say, well, how can we make our model better? So you never actually get to production. Next slide, please. This pattern shows much greater organization. If we look at what happens here, you know, certainly on the front end and the back end, you have clear engagement with data engineering teams. And in the center of the cycle, you have your business experts, your domain experts, and a clear path for getting into the product development lifecycle. One thing to note here is you have a clear exit point, but your exit point is a rewrite and deploy. This is probably a more mature process because at least there's some clarity around some of the owners. But once you get into this loop, you could be in this loop for a very long time. And we work in this process from the assumption that all the code that's written is going to be thrown away. And the work that the data scientists do is ultimately going to be rewritten in a production grade language or by a production grade team. And that introduces significant risks in time. Another thing to take away from this is there's no clear path for iteration. Once you get your model out into production, how do you actually, what's the process by which you circle back into the process to add more features, to retrain your model? It ends up being a very heavy lifting process, particularly if you go back out, if the data science teams are going to write in one language and your deployment happens in another. Finally, while we do have engagement from the business and the product owners, other stakeholders is less clearly defined. What is the appropriate time in this type of a scenario to engage with front-end developers? And how is your model going to be incorporated into the finished product? Those are all very nebulous in this scenario. So while we can certainly expect that we would get products, a digital product likely out of this, there are clearly gaps. Next slide, please. This takes us to what I think is probably the more idealized state, which fully embraces really agile development process for data science workflows. Notice that in this scenario, we have clear expectations about where and when to engage with different stakeholders as part of the broader team. We can see that we have a digital product owner that spans the entire breadth of the process. Our data engineering teams are engaged certainly at the front end, probably also in development, and you can see that at the top and the bottom of the slide. Our data scientists are engaged at the front end. Business and domain experts are engaged at the front end primarily for hypothesis generation. And then we have this emergent field of ML engineering. In the ML engineering, the role of the ML engineer is really reflective of how to embrace the iterative development approach. We want our data scientists to be writing production grade code, and the ML engineers can help enable that. Engineering is the discipline of building products. efficiently at scale in production. In this scenario, our teams are clearly, we're clearly working in a cross-functional environment. We have clear engagement across all stakeholders. We want to bring these teams together on a regular basis, just like we see in Agile development. This is really the idealized state. I think this is where maybe we show a little bit about what this might look like in practice. Oh, no, okay, we have the conceptual release tools. My apologies, go ahead, next slide. So if we're going to embrace this, this development process, then we need to think about how our tools and practices can align to an iterative development approach. And we accept the fact that we need to be working in a cloud native environment. So we start with Git as really our base platform that we're going to work from. We want all of our code to be housed in Git. And during the exploration phase, we want our data scientists to be able to leverage the tools that they're the most comfortable with, Jupyter notebooks and Kubeflow. So Jupyter notebooks, of course, for exploration and as an IDE, and then also Kubeflow as a way to allocate secure, scalable compute resources for consumption. We also want to encourage our data scientists to start thinking about using branching policies with their code early in the process. We want to get our code into Git. We want to regularly create feature branches and push our work in. As we start to find potential, right, opportunities to build models that we think might add value, then we move into this prototyping stage. This is where our code starts to get more hardened, if you will. We start to develop functions. We take our code that we've been writing in our notebook, and we may have been refactoring it into functions. We want to start to pull that out and convert those into importable Python modules. And then we also want to make sure that we're starting to write tests, something that oftentimes data scientists are a little less comfortable with. As we move from that prototyping stage, now we're getting definitely more comfortable with the value that we're creating, but we have to test at larger scale. So we need to be able to scale out at this point. How can we move into a distributed compute environment so that our code executes efficiently? Becomes even more important to add our automated testing. And as we're moving closer and closer to production, we need to start getting some code standards in place. This is where we start thinking about linting our code using things like Flake8 and Black and the distributed compute environments. We also need to start implementing code reviews and logging our artifacts, because now these are at or near production. And then finally, we move into a run and maintain stage, where really we're seeing less of kind of the development inside of things like Jupyter notebooks. We really have a solid suite of unit tests. We can do automated monitoring and retraining and automated releases. This is really, you know, if we move from this idea of data scientists not writing production grade code to leveraging the code that gets written by the data science team into this type of workflow, then we'll get to production faster in a more scalable, maintainable way. Next slide. So what does a Git-based MLOps workflow look like? And how do we see the data scientists and the ML engineers interacting with one another? If we start from the principle that we want to use Git as a common source for all of our code, during the exploration phase, we really want to be working along this top row. So we can picture a scenario where in an agile development process, we would have a 2-week sprint, and our data scientists would create a topic branch that was aligned to the goals of the user story in that sprint. And they can do exploratory analysis inside of their Jupyter notebook, just like they normally would expect. And they can house their code there. Once a day, twice a day, however much makes sense, push that code into Git. As they get more comfortable, that is, as they start with a small data set in memory, maybe they add more data, they start to write functions that help clean that data set, that help organize that data, denormalize it for potential model training. Then we should start thinking about refactoring that code into a source folder. and importing that as a Python module, just like you would any other module. From there, we need to confirm that our code performs as expects, so you can start writing unit tests, and we would ask them to do that, certainly. But we also have the opportunity to look at different runtimes. If we're running our code inside of Pandas, as an example, and we need to be able to scale it out to larger data sets, then maybe we need to be able to convert that into a Spark or a Dask runtime. And that's where we can leverage things like MLrun for scaling out, monitoring, and retraining and logging. As we have that code now into an MLrun function, then that's a natural step into Kubeflow pipelines, which is effectively this migration down into the ML engineering discipline, the construction of products. And what we see in our teams is data scientists that have an interest in the ML engineering discipline. They can span that gap by moving directly from things like in-memory compute and Pandas into distributed compute with tools like Dask. And it's a very natural progression. Again, so I said, as we move through that release cycle, we're moving now toward the pull request. So we want to be able to issue pull requests into master. And then ultimately, when we're ready to tag a release, be able to push that tag in an automated way back to build our deployment. Okay, so I think this is where we want to maybe share a little bit about what that workflow looks like in practice.
Great, so let me let you take control of the screen.
Can you see my screen?
Yep, we see it.
Okay. So conceptually, what I'll do is I'll just walk through a few of the steps that we see code evolving through as we go from idea to release. This is a standard Jupyter notebook. You can see picturing a scenario where a data scientist comes into the notebook, they import pandas, they read in a CSV file, take a segment of that data, and then simply start doing exploration. So they'll generate the visualizations. They're going to explore this. And as they expand, they're going to start writing functions. What we want to see is, we have a source folder here. Our data scientists can then take that code and write it out into the steps in their function. So this happens to be a start pipeline function. This is an importable function. Other data scientists can load it into their notebooks. But the data scientists working on this project can leverage this as to scale it out across multiple runtimes. Once we have our functions well defined, then we can start to create an Azure pipeline. So if you use Azure for this type of work, then you have the ability to write rules around pipelines for automated testing and deployments. This happens to be a two-step job. In the first step, so this only applies to master and tags. In the first step, we test and lin our code. So we can go out in our agent. We can create an environment that exactly matches the environment that our data scientists are working in. And we can activate that Conda environment, do a pip install. And then just like we would with normal development, we can run Python tests. So we can leverage PyTest, generate reports out of that. So we understand how our code is performing, can validate that it does what's expected. And then in the case of a release, when we're ready to tag a release, this particular example, we have a release that only runs after the pull to master has passed and if we have a tag. So you can see it depends on the previous step. So we can persist the tag name as an artifact out of this, and then we can build our job remotely and deploy it into our compute environment. So what we end up doing is we take our source code that we've written, we can create an MLrun function out of it, attach that function to an MLrun project, and then build a Kubeflow pipeline. This pipeline actually happens to have an exit handler, so if it fails, it will send a notification. And then we can pass in, this is actually exposed through an API, so we can pass in a JSON object to determine what exactly the pipeline does when it runs. We set our workflow, establish a path to save the artifacts from the execution, and we test the run. Then we write a function for deployment. So we can take our project that we've written before, we can load that project in and deploy it with a Nucleo function using the code to function step. Back in Azure DevOps, when we're here at a terminal, when we're ready to issue a pull request to master, we have a suite of these that have run. We issue our pull request, we can see that we get a test and lint. This is on a pull request to master, it runs in 3 minutes. This is just one test, but you select an appropriate number. And then when we tag a release, we have a lint, a test and lint, which runs on an automated way. Now that this is tagged, and you can see that this is tagged from this note right here, 0.1.2, then we get the release to dev. This goes out, it builds our function, and then deploys it into a Kubeflow pipeline that's available to be called through an API. That's what I have here.
Excellent. Thank you, Greg. Go back to the presentation. And we'll go into our second poll. And here we want to hear from you about how you handle deploying AI models from lab to production. And you will see the poll in just 1 second.
Yeah, maybe while people are filling the poll, one interesting point you were telling me, Greg, was about the way you scaled code earlier. You know, can you repeat that? Because I think it was pretty impressive. You know, you're a data scientist that just scaled it about 100 times or something.
Yeah, certainly. So, so as you oftentimes see with data science, the evolution of a data science project, the data scientist will start with a small data set. And we had an example of that. We started with a data set that had less than 15 members in it. And the way that the code was written, we had to iterate through the data. So 1 member at a time. And that was perfectly fine for 12 examples in the data. We ran very quickly, minutes. We scaled that up to on the order of 100 examples. And it was slow in a relatively local compute environment, but when we converted it into a Kubeflow pipeline, that code ran in, let's say, roughly 10 minutes. Because we were able to scale the compute out elastically in a single pod. So I guess a little context here, this was a series of functions that were written to run Pandas, so all in-memory compute. But as I said before, we have many, many customers, many examples that we have to contend with. And we were looking to extend that even further, and we went out to several hundred examples in the data set, and our runtime jumped from minutes to hours. We were up to about 5 hours. So in this idea of leveraging the code that's been written, we could use Dask to take some of the functions that were slower running and convert them into Dask delayed functions. So really, we only changed about 7 or 8 lines of code. And by converting these into MLrun functions and leveraging Dask delayed, now we changed the runtime and went back down to about 5 minutes of execution time with 3 to 4 times the data. So this is an example of, and the thing of it is, we were able to write 1 set of unit tests for the in-memory compute and use the same unit tests for that scaled out code.
Right, and if you compare it with the previous practices you had, was essentially rewriting everything in Scala with Spark.
Yeah.
Wasn't And that's a huge effort. And data scientists are not fans of Scala and Java and Spark.
Yeah, well, and the other thing is, every time you do that rewrite, you introduce risk. Yeah, so let's say your data scientists do write unit tests for their code. Now, yeah, if you rewrite it in Scala, you're not going to use the same testing framework. So you have to rewrite that as well.
Yes.
All of those things add to risk and they add to time.
Excellent. Thank you. We're going to end the polling now. And we are moving to the next part of our presentation. Yalan.
Okay, thanks, R. So let's move to the next slide. Essentially, the flow that Greg was describing is something that we sort of envisioned a while ago, but we like to have customers like Greg that sort of share the vision and the enthusiasm, and also making contributions because some of it is open source. But the general idea is that if you look at the workflow, is that you have a data scientist or a developer that wants to write code. Usually they want to write the code in their own environment, whether it's Jupyter or VS Code or PyCharm or whatever. And while they're doing that, they're running their code, they want experiment tracking, they want data lineage, they want all of that stuff, because when they want to go back in time and figure out why we had such great results, 5 experiments ago, they want to be able to see all of that. And also, if you're a manager, you want to be able to see what everyone is doing and what could have been avoided or learned from. Click next. But at a certain point, we need this thing to run as a microservice, whether it's distributed or non-distributed. Part of the nice idea is that once it's converted to a microservice function that runs on Kubernetes, it can actually scale out to many nodes and spread the workload. And this way you get the scaling if you've done the proper API and integration. So the next thing you want to do is add some requirements, because maybe you ran a job and when it's running on the cluster, you may want to add GPUs. You may want to mount it on some volume to get much larger data, or attach it to a real large-scale database or data warehouse to run data at scale. So the general idea is that you can add some annotations to your code that teaches the system that you want to add those package dependencies or resources, and then you're just submitting that, and something else needs to figure out all those details we mentioned. How to convert it to a container, essentially running a Docker build process and adding all the dependencies. How to convert it to a Kubernetes resource, and again, applying various resources, adding CPUs, memory, scaling it out, creating deployment services, all this sort of hassle that's usually done manually or through scripts could be done automatically. And if we've done a good way of abstracting the workload from the actual way of scaling the workload, then we can just, in a flip of a parameter, run distributed or run on a single container, which is usually not the case. If you want to run distributed, you have to rewrite your code to make it distributed. And while you're running the code in production, you still want to have all this tracking done in exactly the same way. You don't want to use different set of tools for artifact tracking in production or in a scale-out manner versus other tools that are used inside your Jupyter notebook or whatever. Next. Now, after we published those functions, we went over a specific function. What is a function? A function could be a data preparation logic, feature analysis logic, training logic, model validation logic, concept drift detection logic, whatever. It could be many different functions, but we want to break our flow into individual functions because then they're serving as Lego building blocks in assembling a bigger pipeline. And once we have Lego building blocks, we can reuse them. We can build one training function for XGBoost, for example, make it the best, include the best Intel or NVIDIA drivers within the package and all of that. And then someone else can use it for his other project instead of replicating it again and again. So the general idea is that we created functions. Those functions are building blocks. And then a machine learning engineer can come back and take those functions. Sometimes he may want to modify the functions because it's, maybe the data scientist forgot some performance optimizations, maybe forgot some exception handling, and while you're testing it, you find some bugs and you want to fix them. So still you have those function components that could be versioned and modified and preserved in a Git. But when you're building a workflow and an automated pipeline, you essentially want to take all those functions and create a layout or sort of a graph of those various steps and run them on the cluster. Now, this could be done with tools like Kubeflow, as Greg mentioned, and there it could even further be optimized and automated. So we can essentially do this step as an automated step that every time we push a pull request, we can have an automated machine that runs the entire workflow. And instead of testing an individual function, test the entire workflow and measure the accuracy, measures the performance of the model, etc., and responds back in like a Slack message or email or whatever. So again, we can have, if we break it to those 3 different steps of developing locally, converting it to a microservice by the developer, not someone else, because the developer knows the package dependencies and all those things that make it really run. It just usually is lacking the capability to convert it to a high performance microservice. So this is really where tools like MLrun and Nucleo fit in to automate this process. And then someone else may pick those components up and build a workflow. Next. So if we're looking at it from a complete CI/CD process applied to machine learning or MLOps, then we have the first step is the development. Essentially, someone takes a project which may have multiple functions or code elements for the various aspects of this project. He may create a new branch, feature branch. He tests it, whether it's in his notebook or IDE, whatever he feels most convenient with. And then he clicks another command. I'll show you that in a minute. And that automatically makes it a microservice. He wants to run it on the cluster as a microservice just to make sure that it really works in a distributed environment. And maybe there are some pitfalls. Forgot some package that was installed on his Jupyter, but he didn't register as a requirement for the distributed job, etc. And once he feels it's okay, he needs to move to the next step, click, which is the continuous integration part. We're taking that and creating a pull request in Git, and that pull request will usually go in through automated tools like linting and Flake 8 and Blake and all of those tools that automatically examine your code. It goes through manual examination. Some your boss, your mentor will check the code and say, you know what, you forgot some things. Maybe there's a better way of doing something, and this could lead to further iterations of your code. Once you've done that, then you want to test the entire pipeline. So that could be done again automatically. We've talked about it in previous webinars on Git-based operation. I'll show a short demo on that just to refresh everyone's memory. And then once it's passed the pipeline and we have adequate results, we can go and merge that pull request. And if it doesn't, then we go back and iterate further and fix it and make it better. Once we've merged the pull request, we have a stable branch. People don't have to work this way. It's just sort of a recommendation. We usually like having sort of a stable and an unstable branch. So the development is sort of an unstable branch or the latest branch. And we can run various regression or testing tools on sort of this development branch. And this is sort of the continuous integration part. Next, Sar. The next phase is once we feel this development branch, we pulled all sorts of fixes and features from various team members, and we've tested everything as a whole. We see that's cool, and we could move to the next state. Then we can sort of essentially push it into sort of a master or a stable branch. And we like to tag it with the version, so we know that we can go back in time. If things break, we can always go back into a tag. And once we tag it, there could be an automated tool that do the deployment based on the tagging. Once we've done the tagging, like we have with many other tools like Jenkins and other, it will automatically deploy your project, sometimes as a canary. A canary means that not all the traffic is going to go to the new version. Some users, for example, are going to be diverted to the new version. Majority of the users will keep working with the old version. And once we feel cozy with that new version, that it really satisfies the requirements and it doesn't crash, we can go into promoting it into the entire set of users. If we don't and it crashes, we can always roll back the canary deployment and go back to the previous version. And once it's in production, we want to keep having things like monitoring of the actual service, monitoring for concept drift. So if there is a concept drift, we may need to roll a new version or change the data and things like that. So that shows a comprehensive flow for doing development and CI and CD for machine learning. If you start with half of it, it's already a good start. But this is sort of more of a holistic way of looking at it. With that, I can share a demo. So, okay. Do you see my screen, Sar?
Yes, we see it.
Okay, so let's see how we can essentially go through this whole process, very long process, but make it way more agile and simple. So I have a notebook. Let's increase the font here so everyone can see that. In my notebook, running on our managed platform, but could run also from remote, or you can run exactly the same. We've tested it with like SageMaker and some of our competitors' products and Ecolab and every managed notebook that you can think of with some configuration. But the general idea is that you have to import some sort of magic here, which is the sort of a compiler for the notebook. So write a function. Let's assume I want to write a function that opens an archive, which is, let's say, an S3 bucket with some pictures or some files, and I want to load it into the cluster itself. So I can write a simple function. My function can have some parameters, has something called a data item, which is like a data object that we want to pass into the function. We want to document our function. So later on, we can use that documentation. And we just write some code. In our code, we can use a special object called context to do things like logging textual messages, logging artifacts, logging models, accessing secret credentials like passwords without violating security, or all sorts of things that this context object provide us. It's optional, but it's really powerful. So I can just write this function. And the next thing that I want to do, I can test it locally, but just for sake of simplicity and timing here, I'll just show you that we run a single command. We just say code to function. Take this code, essentially this code with this handler called open archive. It will figure it. It will find it automatically. Tell it that it requires a specific image, although there are ways to tell it to just build the images automatically. We may want to document that because this function is essentially going into a marketplace. So we want to put some categories and labels and documentation on that. And then we essentially just created a function. This function is essentially serializing all this information that I mentioned, package dependencies and code and everything. We can even see that as sort of a YAML file, pretty much like a Kubernetes resource, if you're familiar with that. And you can see that also the documentation part is recorded. Essentially, it parsed your function and it figure out all your documentation and typing and all that automatically, no manual work. So then we have this sort of YAML file. But at a certain point, and we can save it, we can export it as a file or save it in a database or in a marketplace. And now we have this microservice that we can run anywhere. What does it mean run anywhere? So we can just go and import that object from a database, from Git, from a file, and just go and first let's check the documentation. So you see all the documentation that we wrote in our doc strings is essentially visible. The next thing we can do is we can just go in and run it and run a job using our function. So we can essentially provide it a parameter, a target directory where we want this to be exploded into or unzipped into. We want to pass it a data item, which is, in this case, it's actually an S3 archive. And there's some black magic that will transfer the file for you and all that because we just chose it as a data object. And then we just want to run this code. And when we run this code, it's essentially doing all the work. We see all the logging, it unzipped the directory and recorded all the information about this run. Nothing special about it. It ran it locally in my notebook. The next thing I want to do is run it as a distributed job in the cluster. So the only thing I need to do is just say run. If you look into the logs, you can see it's actually allocating Kubernetes resources called pods, and it's running in the cluster. You see there's really literally no difference from my perspective as a user if I'm running this function locally in my notebook or if I'm running it on a cloud in a cluster in a distributed fashion. Same logging mechanism, same everything. And everything is recorded, so I can essentially just go and click into the MLrun management, and I can see all the information about the execution. I can see all the logs. I can see all the results. In this case, there weren't results. I can see all the artifacts that were generated, all the inputs. I can even see the code, and this code could be later be reused. So I can just click here, and you see I can see the code that a minute ago was on my notebook. So essentially, I pushed everything into a database, and I can later on reuse it for building greater things. The other interesting thing is sometimes I just want to load this function as a model inside another function or inside my notebook. You can even do that. You can just convert a function to a Python model, essentially load it into your memory, and you can reuse that. Later on, we can take those individual functions and just stitch them in another project. And in that project, we can just, this is like a complete end-to-end pipeline project where essentially I just go to the interesting part. I just take a bunch of functions and I create a workflow, a DAG. A DAG is like a graph of executions. This is, for example, one function is doing ingestion, another one is doing analysis, another one is running training, and then I'm running validation, etc. And if I'm going into, after executing this graph, I can go into Kubeflow, which is managed in our platform, and I can look into the entire execution graph. So I can essentially have each one of those steps be developed as an individual function with its own versioning and lifecycle, and then just assemble all of that into a very complicated pipeline in minutes. And we can also do that through Git. We've demonstrated that in the past, but I can do that through a pull request. I can build the same project as a hook to, this case, GitHub Actions. And when I'm, there is a complete documentation here, I'll throw it into the messages here in a minute, and we'll send it over the Slack. But you can see that I can just create /run in my pull request, and this entire pipeline is going to execute and run all those functions. I can also get it as a nice Slack message after the workflow completed with everything. So essentially, all this very, very complicated workflow that I mentioned before could be fully automated in a matter of minutes. Okay, so with that, back to you, Sahar.
Thanks, Johan. Just pull up the deck.
So that I do see a question there in the messages. Can MLrun new task also have access to databases? Yes, there's also structured and unstructured access. The fact that you have data item also allows you to work with the data frames. There's actually going to be a webinar that we're going to do together with MongoDB in a couple of weeks, I believe, that shows how it automatically connects to like MongoDB Atlas managed service.
And this is a great time for anyone else who has any questions to please ask us in the Q&A channel. We'll also be sharing the link to our Slack community in a few minutes so that everyone can join us, and we're going to continue the Q&A session on Slack. There's also plenty of resources for you guys and lots of code and demos and everything else.
Yeah, I also shared the link for the GitHub Actions demo in the chat, so people can look into that.
Okay, we have a question here about fostering collaboration and getting buy-in from the organization on making a change like this. Greg, can you maybe say a couple words about that?
Yeah, so it's my view that this process, moving into more of an MLOps workflow, is really more of an evolution. I think it's one that many organizations are migrating toward, and it's a cultural shift. It's moving into the mindset that you really want to develop products, and that requires engagement with your business stakeholders. So, I would say if teams are looking to make this shift, look for ways to engage with all the stakeholders that you're going to be working with in an organization to get your model into production, because ultimately, that's where you're going to deliver value, is your model in production as part of as an integrated part of a product.
Absolutely. And Yaron, there's one here for you. How can we deploy multiple model objects in thousands using Iguazio?
That's easy, most are not so easy, but relatively easy on Iguazio, because all the frameworks that we work with are all auto-scaling. Nucleo is an extremely high performance serverless engine for model serving. The same function is elastic, scales all the way from 0 to any number of computation elements. It's already used by many people. There was some announcements from NetApp, how they're processing 10 trillions of messages a month using that. And the same function can actually host multiple models. So if you're using GPUs or something like that, you can essentially share the same GPU across multiple models and make it very cost effective.
Excellent. Thanks, Yaron. We'll take one more question here, and later we'll move over to Slack. What are the minimum parts of the MLOps diagram that you think every team should implement?
I think that's a good one for Greg.
Of the MLOps diagram, if you're struggling to get anything else implemented, I would start with getting your code in source control. I think from there it begins to be a much more natural progression once you have your code in source control. If without that, then any efforts to automate your workflows are pretty much blocked. After that, then all the other components begin to open up. I think that's the first step.
Thank you, Greg. So we are nearing the end of our webinar, and we really hope that you found it interesting. We wanted to invite you to learn more about MLOps on our website. We have lots of resources, blogs, videos, including some of industry experts from Netflix, the New York Times, Uber, and others sharing their experience with MLOps projects and letting us know what worked and what didn't. On our website, you can also find all of the previous sessions of the MLOps Live webinar series, and you can watch them on demand. And we'd love to have you join our next session, where we'll take a deep dive into churn prevention use cases, especially first-day churn. But before we move on, we will share the poll results with everyone. So I hope that you can see the poll results from the first question on how people are currently handling deploying AI models from lab to production. And most of them are still looking for a good solution, which is actually very much aligned with what we are hearing from most of our customers and partners. And for the second question, what your current process of collaborating across data science, engineering, and DevOps looks like. 50% of the people who filled out this form says that they have teams that are partly collaborating, which is very interesting. So with that, we'd like to thank everyone for joining us, and thank you, Greg and Yaron, for the great presentations. And we do want to invite you to let us know what you'd like to hear about next, if there are specific topics that are of interest to you. And we invite you to join us on Slack for the Ask Me Anything session so that we can continue the conversation. Thank you, everyone.